Hello, this is Mr. McGovern, and in the 7th video in this Energy and Work series, I'm going to do an example from an NCEA paper. So this example is taken from mechanics paper, which is the code AS91171, and it's the 2020, and it's question 3D. So Joe and Alex wonder whether a compressed spring from a bridge would accelerate their car once the spring is released, as in the diagram below. They decide to determine the effect of the spring on the car's motion, and they estimate for the spring a force of 50,000 newtons would compress the spring from 6 to 4.2 meters. The total mass of the car and its occupants is 1,600 kilograms. So calculate the maximum speed to which the spring could accelerate this car and its occupants if it was compressed to 4.2 meters. You should start your answer by first determining the spring constant K and what assumptions have you made in this calculation. Okay, so the reason I know this is an energy question and I want to attack this with energy is springs seem simple, but they're complicated. Right? Once you push this car into the spring and you let it go and let it uncompress, each millimeter the spring uncompresses, it applies slightly less force, right? Until it's completely uncompressed, then it applies no force. We're used to dealing with things, especially with forces, where there's a constant force being applied the whole time. So because the force on a spring is changing, depends on how compressed and uncompressed it is, forces is very difficult to use unless you're going to use calculus, which we don't do at a high school level in physics. So the way we attack it is we use energy, because energy is useful at just looking at a before situation and an after situation. The before or position A situation is when the spring's compressed, and the position B is when it's completely uncompressed and the car's moving at its maximum speed. So that's what we're going to do. So we've got our system here, which is the Earth. We always put the Earth in case we have to deal with gravitational potential energy, the car, the spring, and the track. Alright, to start with, in position A, when the spring's really compressed, I think it's only got spring energy. And then once it's completely uncompressed and the car's moving, I think it only has kinetic energy. So from our bar chart, we've got an equation. Spring is kinetic energy. Once we've got that equation, we can kind of throw the bar chart away and just deal with the maths. So the formula for spring energy is half kx squared. The formula for kinetic energy is half mv squared. And then I'd try and solve this. They want me to find out the speed, v. I've got m, I've got the mass, I've got x, how much it's compressed to, but I don't have k, and this is why they've said, hey, you should start your answer by first determining k. So I need to figure that out. And the way I'm going to do that is I'm going to draw myself a diagram just so I know what's going on. So they say the spring starts off at 6 meters and then it gets squashed down to 4.2 meters. Okay, so it's been, in my mind, compressed by 1.8. I can use the other spring equation, which is a force equation, to work out the spring constant. So the force applied to squeeze at that 1.8 meters down from 6 to 4.2 was 50,000 newtons. And there's my x is 1.8, and I can just rearrange this to find k. Notice I've dropped the negative, and the negative's in there because it just explains that when I compress the spring down, and to do that, it changes its length to the left, the spring is trying to push to the right. The negative tells you that the spring, the force the spring applies is in the opposite direction to which way it's compressed. So I can just drop it to work out the numbers. So rearrange this and I get K is 27,000 newtons per meter. So now I can go back to my energy equation that I'd worked out before. I've got all the information now. My K is 27,000, my X is 1.8, that's going to be squared, and I've got my mass and I need to find my velocity. So put this in, I get this as v squared, and square root that, I get v equals 7.5 meters per second. What assumption did I make in this calculation? The assumption I made was that the spring energy was converted all to kinetic energy. So I assumed that no energy has been lost to thermal energy. I couldn't just say I assumed that energy is conserved, because energy is always conserved. It's a law of physics. You can't just assume that. It always happens. But some energy in that conservation could be given to another less useful form, like heat, and then the kinetic energy wouldn't be as high. So in this case, I've assumed that there's no thermal energy. All the spring energy became kinetic energy. I hope that helped.